This
Okay, from yesterday class, we discussed about a dynamic routing protocol called OSPF. We discussed about how the OSPF neighborship is formed, what are the conditions to become the OSPF neighbor, what are the stages that the neighbors has to pass through to become the OSPF neighbor, and what are the areas in OSPF. And we discussed about how the neighborship is done with the OSPF process ID on the lab. We have seen creating two buildings with two different networks, like 10 network and 20 network, and then we make them communicate between the buildings using the OSPF protocol. So that is about OSPF. Any questions from our previous class?
Yesterday, you told that you will be explaining about the multiple multiple routers, right? On the OSPF in the lab. Yeah.
Multiple what?
Multiple route. If we use the multiple PCs, I mean not in one network. If we use different networks. Yesterday night, you said that you will be doing it in today's lab. First, you'll be starting with that, and
Oh, okay, got it. So we wanted to see one more router in the area and then see how it is seen in the other side, correct?
yes, exactly.
Okay, let's do that. Let me open the previous lab. Okay, I'm gonna share the screen. Uh,
Ravi sir, my friend is waiting in waiting room, sir. Please join. Sorry.
okay, I admitted him.
Thank you so much.
So let's see the config. Finance, airport, copy that is available here. So hold on a second. All right, so I had to increase the number of ports on the router so that I can connect the another router in the network. So that's what I did. Now I'm gonna repeat the same steps what I did yesterday in building the OSPF and making the neighborship, and then we'll see, we'll add one more router. So here, let's see our configs are still there or not. So run pipe section OSPF. Okay, OSPF config is there. So here, let's do the same thing. Router 4. Router OSPF 1. At least one interface should be up. Okay, let me go ahead and bring the interface up. So this one should be up and this one should be up. Let's go ahead and bring up these interfaces. It should be that, right? So will be interface 3. Interface is 0/0. 0/0. No shit. Let's see. Okay, so this one is interface 0/0. IP address 30.0.0.2. 255.255.252. 252. No set. Yeah. And then interface 0/1. No shut. This is 0/1. And interface is 0/1.20. IP address 20.0.0.1. 25.255.0. Encapsulation .1Q20. No shut. Cache show IP interface brief. 20 network. 30 network. Let's bring up the OSPF router OSPF 1 network. .0.0.2. 0.0.0.3. Area 0. And then similarly network 20.0.0.1 and 0.0.0.255 and then area 0. Now show run pipe section OSPF. So here, if you observe, I'm creating two network statements. Network statement 30.0.0.0, 30.0.0.2, and then 20.0.0.1. I'm putting them in the area, and to check the neighborship, I have to show IP OSPF neighbor. Okay. So the neighborship is up. We are able to see both the neighbors are up between the routers, between the buildings. So now let's see if the PC0 is able to ping the PC2 in the other gateway or not. Okay. I'm going to the PC0. Trying to ping 20.0.0.10. It says destination host unreachable, so it means that it is not working. So let's see why it is. But it says it's trying to go 10.0.0.1. So now let's go here and check the OSPF neighbor and check the route. Show IP route. It has only 10 dot network. It doesn't have the 20 dot network. So let's go here and check the show IP route. It has a locally connected route. Okay. Let's see if we're able to ping this one. Ping 20.0.0.10. It's pinging. Okay, let's see the 20 network here. Still not learning the network here. Let's go ahead and check. Show IP OSPF neighbor. Show IP OSPF database. Does not have 20 network in its database. So let's check the OSPF configuration again. Network is injected, but it's not. So I'm going to do clear IP OSPF process. So I resetted the OSPF neighborship. Okay. Now let's wait it to come back up. It's up now. Let's go ahead and check the routes. Go the route. Still not injecting the 20 dot network. See. Show IP interface brief. 20 network is up. Yeah, 20 network is the /24. /1.20 APOs, PF, IP OSPF database. IP route. It's learning that route now. So now let's go ahead and ping it. Okay, so this part is done. Now we are the same place where we were done till yesterday. So PC0 on the left hand side is trying to talk to PC2, it's pinging. That is what we proved here. So ping 20 network. So from PC0 we were able to ping the PC1 in the building B. I'm gonna ping the PC2. Okay, first packet is broadcast packet, it failed, and then you're getting a response back. So now it should be working on all the packets. Okay. So now there was a question yesterday that if we connect one more router, and then how does this router will see these routes coming from this router, right? So let's put them. Let's bring up the OSPF neighborship between these two routers now. Let's use a 40 network here. This should be 40.0.0.1, and this should be 40.0.0.2. Let's bring up the OSPF neighborship between them. To bring up, let's bring up this interface first. (0/2), 0/2, IP address 40.0.0.1, 255.255.255.252. No shut. And similarly, this one. Gig 0/0/0. 0/0/0. IP address 40.0.0.2. So these two links are up. Now let's try to ping the neighbor in 40.0.0.1. Okay, they both are reachable. Now let's bring up the OSPF here. Router OSPF2. Network statement 40.0.0.2, 0.0.0.3. And then let's make it as area 1. Okay. Similarly, this one, let's go ahead here. Router OSPF1, network statement 40.0.0.1, 0.0.0.3, area 1. Okay, so technically what we have done is this is all area 0 until this point. Okay. This is your area 0. And this point is area 1. Okay. So now let's go ahead and check the routes learning from here. Let's check the border router first. How do we see those routes? Okay. So let's go ahead and check on the border router. So this is the border router which is connecting both the areas, right? So now you can do show IP OSPF database. So you will see area 0 routes, which are 30 network. You'll see area 1 routes, where you'll see area 1, which has the 42 dot link ID, and the area 0 has 30 network link ID, is what you're observing. And if you observe here, you'll still see the 40 network. Yes, you're seeing the 40 network here on the left hand side, but it says OIA. OIA means, if you look at here, it will show you OSPF inter area, meaning that route is learning from a different area, not in the same area. So you will see OSPF inter-area route. But if you observe the local route, like a local OSPF 20 network, it is directly connected as a OSPF-O route, which is internal to the area, which is learning from the area 0. But this one, area 1, is a 40 network, and if you go ahead and check it here, that is inter-area route, which is OIA. So that is how you will see. Is that clear now?
Yes.
Okay. All right. So I'm gonna save it. Okay, let's look at the time. Okay, so we will talk about EIGRP, but I don't think we have enough time to start or complete. But we'll start EIGRP, we'll see where we can stop, and then we'll continue EIGRP in the next class. So let me bring up my own whiteboard. Just like OSPF, EIGRP is also a distance, EIGRP also a dynamic routing protocol. But EIGRP is advanced distance vector protocol. So, RIP is a distance vector protocol. It works on the best path with the number of hops, but it does not care about other parameters like delay. What is the speed that the packet can be flowing? That is not worried by. That is not calculated by the RIP, but EIGRP is enhanced interior gateway protocol. It is advanced, as I told you, because it can calculate the best path with various conditions in mind. So EIGRP works on calculating the best path by 5 parameters: bandwidth, these two can be interchanged. So I'm going to put the delay here and then put the load here, and then the MP here. Okay, so these are based on these 5 parameters. The EIGRP calculates the best path. Meaning, let's say you have router 1, router 2, and router 3, and with the destination so we have a path 1, from R1 to R2, and there is a path 1 from R1 to R3, or a different path from R1 to R3, and there's both go to destination. Okay, in that case, if that is the way the path is taking R1, R2, and then the destination, and R1, R3 to the destination, EIGRP selects the best path by validating all of these conditions. So there is a formula to calculate the EIGRP metric. So just like OSP of 10 to the power 8 divided by reference bandwidth, EIGRP also has a formula to calculate the best path. So those will be represented in terms of the K values. So K values are nothing but an indicator whether to consider the condition or not. If k equal to 1, we are taking it into the consideration. If the k equal to 0, we are not taking into the consideration. That is the basic value. Okay. So the formula for the metric in EIGRP equal to K1 into bandwidth plus K2 into bandwidth divided by 256 minus load plus K3 into delay plus K5 divided by reliability plus K4. So that is the formula. By default, K1, K3 equal to 1, K2, K4, K5 equal to 0. So these are the by default K values, meaning by default we are considering bandwidth and delay as the metric calculation conditions, but remaining the formula will be 0. So metric is equal to bandwidth plus delay. So that is the formula. By default formula, the EIGRP uses. So EIGRP calculates what is the bandwidth of this link, and then what is the delay in getting the packet from here to destination. It will check the bandwidth and the delay, and select, let's say the metric is 50 here by calculating both bandwidth and delay. Let's say the bandwidth and the delay whole calculated here as 40. So whichever has the lowest metric, that path will be preferred to go to the destination. Okay, so that is the formula to calculate the EIGRP metric. Any questions, guys, on this topic?
No, sir.
Okay, so that is how the EIGRP calculate the best path. And similarly, in yesterday we talked about OSPF neighboring conditions. Similarly, EIGRP also needs some parameters to match to have the neighbor conditions. So EIGRP, obviously, just like from yesterday, we talked about EIGRP or OSPF will send a hello message, right? Similarly, the EIGRP does also send the hello message, but this time it will be using a multicast address 224.0.0.10. Yesterday, EIGRP used a multicast address of 24.0.0.5. EIGRP sends a hello message to this group address. So when this router is also running the EIGRP, it will also send the hello message to this group address, and eventually they both will meet on that group, and then they become the EIGRP neighbors. But to become the neighbors, there have to be conditions to be matched. So first condition is they both should be reachable, meaning they both should be on the same subnet. Reachable. So router 1 and router 2 should be reachable. That can be happening when via same subnet. Okay, and next condition is k values. K values should match on both sides. So by default, K1 and K3 will be 1 on this router, and K1 and K3 will be 1 on this router. So by default, K value should match on both routers. So K values on both routers should match on both sides. That is another condition. If you change K values on one router and if you forgot to change, the neighbors will not come up. And the last condition is the AS number. AS number is nothing but the autonomous system number that you define in your company. So that is a value that you can define from number 1 to number 65535. It can be any of that number in that range. So that AS number should match when you're building the EIGRP neighbor. Okay. So AS number should match. These are the 3 conditions that need to be matched for the EIGRP neighbors to be formed. Okay. And coming to the EIGRP AD value of EIGRP is 90 and OSP of EIGRP is 110. If a router has both the protocols EIGRP and OSPF, EIGRP route is preferred because the AD value is smaller than the OSPF. So EIGRP is better on a router compared to the OSPF. Okay. Any questions on the this part?
No, sir.
Okay. Let's talk about EIGRP methodology or how they consider the distances. So there are 2 concepts which are called feasible distance, and the other one is reported distance. So in the feasible distance, let's say this router is getting one path via this router, another path via this router. So you have one more and one more, and you have the destination here. Okay, let's say the distance from R1 to R2, R3, and this is the destination. The R1 to R2 destination is, let's say, 5, and R2 to R destination, the distance is 5, and R1 to R3 the distance is 10, and R3 to destination, the destination is like 10. Okay, so whichever is the lower distance, I mean whichever is the shorter distance to go to the destination, that is the best metric, right? So here in this case, which path is preferred, path 1 or path 2? Path 1 is the above one, path 2 is the below one.
Path 1.
Yeah, so the path 1 is the best distance, right? So the metric of the best route to a network, that is called the feasible distance. So here best path is called feasible distance, which is equal to 10. Okay, and reported distance on the best path, whatever the neighbor that is reporting the distance from it to the destination is called the reported distance. So here R2 is reporting the distance of 5 to the R1. So for R1, the reported distance will be 5. Okay, so feasible distance is the best path that is used to reach the destination. Reported distance is the metric advertised by the neighbor router for the specific route. So it is the metric that is advertised by the R2 pointing to the R1. So here feasible distance is the distance from R1 to R2 plus R2 to destination. That is the feasible distance. But the reported distance is the R2 to destination. That is 5. Is these two terminologies clear?
Yes.
Yes, sir.
Okay. So these are the two distances that we talk in the EIGRP. But there is also called as the paths. So what is the primary path and what is the secondary path? So whichever is the best path, that is called the successor path. Best path is called the successor path. Okay, second best path is called feasible successor path. In our example, path 1 is the successor path. Path 2 is the feasible successor path. So you need to understand these 4 terminologies in EIGRP that are important. Feasible distance is the best distance to reach the destination. Reported distance is the distance that is reported by the neighbor to reach the destination. Best path is the successor path. That is the best path available to reach the destination. Second best path is called the feasible successor path, which is also called as the backup path. Clear? Let's do a simple diagram. Okay, tell me feasible distance, reported distance, successor path, feasible successor path. So this is path 1. This is path 2. This is path 3. Put your answers in the chat, please.
Feasible distance is part 1. And
Put it in the chat.
Okay.
Yeah, so let's look at the best distance. So this distance is like what? 25. Path 1 distance is 25, the entire path. Path 2 distance is 50, 60. And path 3 distance is 140. So best path is path 1. So that can be called as successor path. Second best is 60. That is feasible successor path 2. Feasible distance is the best distance, that will be 25. Report distance will be 20. Right? R2 is reporting 10 plus 10, 20 to the R1. Report distance is equal to 20. So whoever got 25, 20, path 1 and path 2 is right. Whoever got 25, 10, they're all wrong. But most of them got successor and feasible successor right. 25, 20, path 1 and path 2. Okay. Is that clear, guys? Any questions, guys? You guys hear me?
Yes.
All right. I'm going to stop it there. I'll do the EIGRP lab in tomorrow's class. Don't have any questions? Thanks for joining today.
Thank you.
Thank you.